So welcome to Quick Game Development with CppCon2014 and 14. Again, thank you for coming. Before we begin, I'd like to introduce myself. My name is Vittorio Romeo. I'm a computer science student at the University of Messina, and I've learned programming and C++ as an autodidact. My interests cover software development, gaming, and game development, and also something I'm really passionate about is sharing my knowledge. I've created several video tutorials and articles and open source code bases that I like to share with people to help them learn new things. So about this talk, I'm gonna divide this talk in two parts. In the first part, we'll talk briefly about game development, why I think every one of you should try at least once game development, and why use C++, and why use the latest standards. And in the second part, I'm going to try something a little different. I'm going to have a live coding part with several code segments that I've prepared. And we're going to walk through all those code segments and compile them and show you the process of the creation of a simple video game. So what I want to achieve with this talk is basically encouraging everyone to try out game development and demonstrating how easy it is nowadays with the newest standards and the libraries that are available for free. Game development is what I like to call an all-around development experience. So how many of you have tried game development in the past? Nice. So it's about more than 50%. So I call it an all-around game development experience because game development involves the programmer with a lot of stuff. So if you're making a game alone, you'll have to take care not only of the code and the implementation, but also the design and the creation of the resources. If you're in a team, you'll have to interact with people that work on other kind of creative resources like graphics, music, and sounds. And also, you always learn new things by developing games, like techniques for networking, physics, and so on. It really involves a lot of different subjects. And also one reason that I didn't write, but I think is very important, is that game development is fun. You see, you make a change in the code and you get instant feedback. And also if your game is fun, your concept is fun, you will enjoy developing it and playing it. So why C++ for game development? This is a subject that has been covered a lot in the past, but I believe that the most important reasons are efficiency. In fact, C++, as we all know, allows us to create zero-code abstractions, and that's very important because performance is one of the keys for a good game. Also, C++ is really portable. You can target a lot of different architectures, and most of the time you don't even need to change your code. And C++ is also widespread, and by that I mean that there are a lot of libraries and resources available that can help the programmer with their game. So why use CppCon11 and 14 for game development? All of these features have been covered a lot in the past, so I'll try to show you some real-life examples that I've actually used in my own games. For example, lambdas, variadic templates, and decal type were really useful in the creation of factory functions, like for different types of enemies. Or for callbacks, I've used them in my collision engine, so that when a collision happened, a lambda would, it will fire a lambda, and there will be an interaction between two entities. Then there is a very important thing that is made much easier thanks to the new standards, and is memory management. With unique pointer, it's very easy to manage the lifetime of entities. With shared pointer, I manage the lifetime of resources very easily because we can share resources between different parts of the code. And also something that I rarely hear about is offset off, which was introduced in C99, and it's now standard in C++ with CppCon11. And I've used that in an entity management system to basically allocate some more bytes for every entity and get a Boolean flag to decide whether or not the entity had to be destroyed. Also, there is a fantastic header that was introduced again in CppCon11, which is Chrono, and I've used it frequently for game loop timing and getting the frame rate right. All of the other features that I didn't cover are extremely useful and extremely convenient, but as I already said, they have already been talked about a lot in the past, so I'll just go forward. So let's get started. Our goal is creating an Arkanoid or Breakout clone from scratch, and step by step, I'll demonstrate how easy it is to create it, and the end result will be around 200 and 300 lines of code. So the compiler we're going to use requires obviously C++11 support, but since we're going to use some C++14 features such as generic lambdas, we need a C++14 compliant compiler. And my compiler of choice is Clang, which fully supports the C++14 standard. But G++ 4.9 also supports all the features we're going to use in this talk. As for external resources, we're going to use the SFML library, which is a very simple and fast library for interfacing with the input system, the audio system, and the graphical system. And it makes rendering sprites and 2D objects to the screen very easy. It also manages the windows and mouse and keyboard. So it's a very useful library. And if you want to, you can follow this talk on your own laptop. You can download all the code and the slides on that GitHub page. And the library is available on that website and on most package managers if you are using a Linux distribution. So now I'm going to switch to the code. And during the code explanation, I will also switch back to the slides to show you some diagrams. So the first thing to notice is I have a simple compile script that basically links SFML and starts immediately the executable we compile. It's very easy. And let's begin the development. So I'm going to start with the creation of a simple empty window. The first thing we're going to need is the inclusion of the SFML graphics header, which includes all common STD classes such as vector and so on, and also all the modules required for the window management. I defined some constants here for the width and the height of the window by using the const expert keyword to make clear that these are not going to change. And in the main method, I create a window by using the SF render window class, which is basically a class that allows you to draw graphics on it. It takes in the constructor a vector2 parameter, which is a vector in the mathematical sense of 2 unsigned integers, and these are the sides of the window, and also a title for the window. Next, something important is setting a frame rate limit so that we can make sure our game will run at the same speed on every architecture. This is, it's an hack. There are many better ways to do this, but for the scope of this talk, it's appropriate. Next, we're gonna create the game loop. For those that are not familiar with game development, basically the game loop is what allows the game to continuously run, and it's the core of the game. It is composed of 3 phases, usually. The first phase is getting the input from the keyboard or the mouse. The second phase is updating the game logic, such as the entities. And the third phase is drawing the game entities on the screen. So this kind of loop is very easy to implement. We just use a while true. And in the first step, we clear the window by removing all the graphics that were displayed in the previous frame. And then we check using SFML if the escape key is pressed. And this is the input part of our loop. If the key is pressed, we just break out of the loop and stop the program. And another required thing is calling display on the window object so that we can show the window's contents. I wanted to tell you that if you have any question about the code, I'm happy to answer them. And also, if I'm going too fast or too slow, please tell me. Yes?
I was wondering if there's any advantage of using the event class for SFML, because I've traditionally used the event and says while you process the event.
Yeah,
Is there any advantage of using that?
So the question was, is there any any advantage in using the SFML event class? So SFML has another way to gather input, which are events. Basically, you use a loop to query all the events that are coming from the operating system to the window. and it can be used to manage input. So the difference is that events, I mean, you can do the same thing with events and global objects. Events are a little more verbose, but also are more flexible. But for this scope of the talk, we will simply use the global objects. So it's a convenience factor. So let's close some terminals and compile the first segment. So as you can see, we have a blank window, and we can close it by pressing escape. Not very interesting. Let's move on. So in the second segment, we'll actually create our first game entity, which will be the ball. So I'm going to use classes, obviously, to represent every single game entity type. And in the ball class, I begin by defining some public constants, using always const_exp where possible. And the first constant will be the default color of the ball, the second constant, the default radius, and the third constant, the default velocity. So SFML offers us the possibility to render simple shapes such as rectangles and circles and convex polygons with the shape classes. So I simply have a field called shape of type circle shape. And by setting the radius, the color, and the size of the shape, I can simply render it on the window and make it move. So it also stores the position. Another thing we're going to need is a vector of floats, which will hold the current velocity of the ball so that we can alter its direction and speed. The constructor will simply take the starting coordinates of the ball that will usually be in the center of the screen. And here we will simply set the shape's position, shape's radius, the color of the shape, and the origin, which is basically the point from where we will move the ball. I have another diagram, which is very simple, but this is the coordinate system of SFML. It is different from other libraries such as OpenGL, as they use the origin in the center. SFML uses the origin in the top left corner of the window. So let's start thinking about the design of our game. Every single game entity type will have two methods. There will be update and draw. This is a very basic design for a game. And in the update method, we will simply move the ball. SFML offers us a move method on the shape that will take a velocity vector and continuously add it to the position vector during the frames. I have another diagram for that. Very simple again. Every update, the velocity vector will be added to the position of the ball, and during the time, it will look like the ball is moving. It's very simple. In the draw method, we'll actually take a reference parameter to a render window that will be the target where we're going to draw the object. And we're simply going to ask the target to draw the object on it for us. We'll also have to initialize the default color data member outside of the class because of the language. So in the main function, we create an instance of the ball, and in the constructor, we pass the center of the window. And now, in the game loop, we have to call the update and the draw method of the ball. So basically, this line is the update phase of our game, and this other line is the draw phase of our game. We have everything that we need, so we can compile and test out this segment. So as you can see, we have a moving ball on the screen, but unfortunately, it goes out of the window. We need to find a way to prevent that. And we'll do that in the third code segment. So the problem that we're facing here is that when the ball is going out of the window, we need to make it bounce. So first of all, we need to check whether the ball is going out of the window and in what direction. To do that, it's a very simple comparison between the right bound of the ball and the width of the window. To get the right bound of the ball, we simply add the radius of the ball to the x coordinate, which is in the center. And we check if it is greater than the width of the window. And the same idea can be applied for every single other direction. So the implementation is very simple. To begin, we need some getters that will help us get the different bounds of the ball, because we're going to use those very frequently. So we can get the x, y coordinates, the left, right, and top and bottom bounds. So all of these methods are const and no except, because they are very simple and they're likely to get inlined and optimized by the compiler. In the update method, we basically need to keep the ball inside the window. And the best way of doing this and dealing with any kind of collision detection and response is moving the object regardless. Then if the object collided or went out of the window, solve that. So we always move the object regardless and then solve the collision. So after moving the ball, we can find ourselves in 4 different situations. Either the left bound of the ball left the window, so the left coordinate is lower than 0, so we need to make the ball bounce horizontally towards the right, and to do that we set the x component of the velocity vector to a positive value, or it's going out to the right and we set the x value to a negative value, or we have the situation where it's going out vertically, and it is the same exact idea. And the rest of the code is completely the same, so let's compile and try it out. As you can see, the ball now bounces and doesn't go outside the window, so it's working. In the fourth code segment, we'll actually add the paddle, which is the little rectangle that the player will control. And to do that, we create a new class, like we did for the ball, and call it paddle. We have some constants here that have the default width, height, and velocity. And I also have a different kind of shape here, which is rectangle shape, not circle shape anymore. And the interface is almost the same. There are some differences because obviously there is not a radius, but there is a width and a height. So you have to change some lines in the constructor, but it's very easy and straightforward. So in the update method of the paddle, we'll call another function that will process the player input. And this function will alter the velocity vector based on what the player is pressing. So if I'm pressing the right arrow key, it will set the velocity vector as x component to a positive value. And then after coming out of that function, we will move the shape with the new velocity vector. So this is the process player input function that we're going to call in the update method. It's very simple. Basically, we query the state of the keyboard, and we check if the left key is being pressed. Also, we need to make sure that the paddle won't go out of the window, either to the left or to the right. So we will only move it to the left if it's inside the window to the left. I hope it's clear. Basically, we check if the left coordinate of the paddle is inside the window, and if it is, we move it to the left. Otherwise, we do nothing. Then we check also the right arrow key and the right direction of movement. And if no arrow keys are pressed, we set the velocity to 0 to stop the movement of the paddle. In the main function, we do the same as we did for the ball. We create a paddle instance. And this time it's not in the center of the window, but it's a little higher than the bottom corner of the window. And in the game loop, we update the paddle after the ball and draw it. So it's the same design as we did for the ball. Let's compile and try it out. So as you can see, we have this rectangle that I can move with the left and right arrow keys, and it cannot go outside of the window because of our checks. But there is no interaction between the rectangle and the ball, as you can see. So we need to fix that. So in this code segment, we'll actually deal with the interactions between the ball and the paddle. The first thing we have to do is create a generic function that helps us understand when 2 objects are intersecting. As you may have noticed, I'm using a rectangle collision bound even for the ball, because for the scope of this game, it's okay. It's not going to be noticeable. And we're going to do a test that's called AABB versus IABB. I have a diagram for that. So AABB stands for axis aligned bounding box, and it's basically a rectangle. And we can check if 2 AABBs are overlapping by doing some calculations and some Boolean ANDs on their values. So we basically calculate a vertical overlap and a horizontal overlap by subtracting the opposite x and y bounds, like we subtract the first object's right bound from the second object's left bound, and the same for the vertical bounds. And if there is a positive value in both of horizontal and vertical overlap, it means that the objects are actually colliding. And so in the code, this looks like this. We simply check that this is the horizontal overlap, and this is the vertical overlap. As you can see, we have 3 hands that chain this together. So if all of these conditions are valid, the objects are intersecting. I hope that's clear. So we also need another function that I will call in the update phase of our game loop that will actually check if the paddle and the ball are colliding, and if they are, it will try to resolve the collision in a realistic manner. So this function takes a constant paddle parameter because we are not going to alter anything about the paddle, and it also takes a reference to a ball, and it's not const because we're going to make the ball bounce, so we need to change its velocity. We begin by checking if these 2 objects are intersecting. If they are not intersecting, we'll simply go out of the function. Otherwise, we simply set the ball's velocity to a negative value on the y-coordinate so that it bounces towards the top of the window. Then we have to do something a little more interesting. So in this kind of games, the collision between the ball and the paddle is very important, and the player usually expects that if the ball has hit the paddle on the right side, it will bounce to the right. So to do that, we simply check whether the ball hit the paddle to the right of its center or to the left of its center, and make it bounce in that direction. It's very simple. We check basically if the center of the ball was lower than the center of the paddle, and based on that, we change the velocity either to a negative or to a positive one. And in the game loop, it's almost the same. We just add this function that is called every frame. So every frame we have to check for collision and solve it. As you can see, I can move the paddle, and there is an interaction between the paddle and the ball. Let's move forward. Now we're still missing a fundamental game element, which are the bricks. And we're going to create a class for them, as we did for the paddle. It's very similar, as they are both rectangles. We're just going to add a new field, which is destroyed, in place of the velocity field. And it will be used in the following code segments to mark the destroyed bricks and remove them from a vector. There is nothing in the update method, but we'll use it anyway to keep the interface the same. And that's it, basically. Now I want to create these bricks in a grid-like fashion. So I need a vector of bricks because we're going to have multiple instances. And I'm using some constants to decide how many bricks I want, how many columns, how many rows, what column number should I start creating bricks, what row number, and also the spacing and the offset between the bricks. Now with a 2D for loop, I can loop through all the rows and the columns, and I can simply place back a new brick in the brick vector using the variadic constructor syntax. And the x and y coordinates are calculated using those constants. And in the game loop, to follow the same interface, we need to update all the bricks and draw all the bricks using 2 C++11 for loops. We're taking them by reference, obviously, so that we don't make unnecessary copies. So let's try it out. It was the 6th segment. As you can see, we have the creation of the bricks in the grid-like manner, but there is no interaction between the bricks and the ball. In this segment, we'll actually have the ball collide with the bricks and respond to the collision and destroy the brick. So all the classes are the same. We are just going to add some new code here in the, as a free function, and it is called solve brick and ball collision. It will take a brick by reference and a ball by reference, and not non-const references, as we're going to change both of these objects. So the first thing to do is check if the objects intersect. If they are not intersecting, we go out of the function, as we did with the paddle. Otherwise, we mark the brick as destroyed. Now, we do this instead of directly destroying the brick, not only for performance reasons, but also because we might have some kind of interactions that access the brick during the game loop. So we don't want to access a null pointer or some kind of memory that was deleted. Then we're gonna have some complex calculations here that allow us to make the ball respond realistically to the collision. The first thing we have to know is the direction the ball hit the brick in. So this is done by calculating the overlap from every direction. You calculate how much overlap was there from the right, how much overlap was there from the left, the top and the bottom, and you get the minimum values. By getting the minimum values, you understand what direction the ball actually hit the brick. As you can see here, since the overlap right is much smaller than the overlap left, we can safely assume that the ball hit the brick from the right. And we do this for every direction. We get the overlap, and then we have some Boolean values here that will tell us if the ball came from the left or from the right. And we check that by basically taking the absolute value of the overlaps and comparing them. So in this case, if overlap right was minor than overlap left, this Boolean will be false, and we will know that the ball came from the right. So we can respond to that. Then we have to check whether the horizontal overlap is less than the vertical overlap. This is done because we don't want the ball to bounce in two different directions. Basically, if the ball hits the brick from the bottom, there is still going to be a horizontal overlap, but we do not care about that because it will be obviously bigger than the Y overlap. So we take the minimum overlap. I hope that's clear. Do you have any question? Okay. So we check whether the horizontal overlap was less than the vertical overlap, and based on that, and on the direction we previously calculated, like from the left or from the right or top or bottom, we alter the velocity of the ball, either on the X coordinate or the Y coordinate. Now, as you may remember, we have all of our bricks marked. And first of all, we have to check the collision between the ball and every single brick. So we put that a function call inside the for loop. Then we'll have to erase from the vector all the bricks that have been marked. We can do that with a standard algorithm, which is remove if. It's very efficient. What remove if does is basically it shifts and rearranges all the elements of a container so that the elements that satisfy a certain predicate are put toward the ends of the container. So after that, we call erase on the bricks vector. The first parameter we're going to call erase with is the result of the remove if function, and that will be an iterator to the first object of those that satisfy the predicate. So if you think about it, we put all the destroyed bricks towards the end of the vector, and we get the iterator to the first one. And after that, we use the std end to get the end of the vector, and we delete from the vector in one single instruction all the bricks that are at the end of the vector and satisfy the predicate. So this is a very efficient way and safe way to deal with entity destroying, because it is fast and also allows us to interact with the destroyed bricks before we destroy them. So if there is an interaction between if there is any simultaneous interaction that wants to destroy the same brick, there is no trouble. We won't access a destroyed memory object. Let's try it out. Okay, as you can see, the ball reacts to the bricks, and we can destroy them easily. So we basically have a playable game, and it's about 200 lines of code. But we have a lot of code duplication, and we need to spend some time refactoring the code. So the second part of the live coding will start with simple refactoring, and then in the last two segments, I'll show you how we can generalize the game architecture to allow the programmer to easily create new game objects, and we'll use an interesting architecture with a manager, entities, and polymorphism. So to begin our refactoring, we notice that we have two rectangles that are the bricks and the paddle. and they have the repetition of the same getters. So we simply put them in two different classes, one for the rectangle that with all the shape itself and all the getters, and one for the circle. It's very simple. And these will be used like mixing classes. We simply make the ball inherit from the circle class, and the puddle and the brick class inherit from the rectangle class. Very simple. So we save a lot of lines, and we avoid some code repetition, and it is exactly the same. So now that we've done this, I wanted to show you some diagrams here that will help us understand what we're going to do. So we want to have a nice architecture that will help us expand our game easily without having to always add stuff to the game loop. The basic idea is that we will have a base entity class that will support polymorphism, and also these two mixing classes that will tell us what the shape of the objects are. Every single class will derive from entity, and the puddle and the bricks will use inheritance as a mixin for the rectangle, and the ball we use inheritance as a mixin for the circle. It's very simple. Also, we're going to use some classes to better develop our architecture. We're going to have a game class that encapsulates everything about the game that we can use to restart and stop the game. Then we're going to have a manager class that takes care of entity management. And by that I mean the creation and the updating and the drawing and the destroying the entities. And this manager class will hold two structures. One structure will hold basically a contiguous set of entities under the form of unique pointers to support polymorphism. And the second structure will be an STD map that automatically allows that automatically sorts the entities based on their types using the type ID keyword, and allows the programmer to easily retrieve all entities of a certain type and do something with them. So this will be our architecture. Let's implement it. I start here by creating the game class. So all the code is the same here, and until we get here, which is the game class. So the first thing I want to do is create an enum, a scoped enum, that is called state, and it will help me understand what state the game is in. So it will be possible to switch between the paused and in progress state by pressing the P key. After defining the enum, we need to store some additional things. So here we have all the stuff that we had in the main function, and now they are part of the game class. And we also added a field for the current state, and a field to check if the pause button was pressed the last frame. We need that check because otherwise, if the user was pressing the pause key, it would continuously fire and pause and unpause the game repeatedly every frame. So I added a method to this class which is called restart and allows us to start the game from again. Basically, it sets the state to paused and creates the bricks as we did in the main function earlier, and also refreshes the ball and the paddle by reinitializing them. I also have a run method, which will start the game loop. And in the game loop, we have something new that is the check for the P key. And if the P key was not pressed at the last frame, we basically toggle the status here. And if it was paused, it will be in progress, or vice versa. It's very simple. And when the key is pressed, we set that boolean to true. Otherwise, if the key was not pressed, we set it to false. And that's, as I said, to avoid continuous repetition of the pausing or unpausing. We'll also use the R key to restart the game. And the rest of the code is exactly the same. In the main function, we create a new game object, we restart it and run it. And this is the simple game architecture class. So we can start our game, as you can see, it's paused. By pressing P, we can unpause it, or pause it again. And by pressing R, we can restart the game. Very simple. Now, this is the interesting part. We need a system, as I explained earlier, that will allow us to quickly expand the game and not worry about memory management, the creation of classes, and altering the game loop. The game class is now something that doesn't need to care about the other game objects. So we're trying to use some object-oriented design that will help us do that, basically. We will need the memory header, which is the C++11 header for smart pointers, as we're going to use unique pointers. We'll also need the type info and map header to group entities by their type and allow the programmer to get them easily. So the first thing we're going to do is create a polymorphic base entity class. This entity class will hold the destroyed Boolean so that we can easily remove all marked entities in the manager class, and also it will hold the virtual destructor to enable polymorphism, and a virtual update method and a virtual draw method. So this kind of design is very primitive. There are much better ways to do this, but for the scope of a small game such as an Arkanoid clone, it's very easy to implement and it works very well. So basically in our game classes, we're just gonna override those methods with their game logic and drawing logic. Now we need a manager that will help us store and manage all of these entities. As you may recall from this diagram, we need two data structures. The first one will be a simple vector of unique pointers of entity, and this will actually store the entities. This will own the entities. Then we'll need a map that will take an unsigned integer as the key. I use size t because it's what the standard returns for the type info. And for every type hash code, the type ID, it will store a vector of entity pointers. As you can see, there are row pointers, non-owning pointers. And this will help us gather the entities in groups. So to populate and query these data structures, it's a good idea to create methods that will help us. So I'm using here variadic templates to create a create method that will take a type T manually specified by the programmer, which will be the entity type, and it will deduct some arguments that will be forwarded to the constructor of the entities. We begin by statically asserting that the T type we're passing to this method is actually derived from entity. Then we'll create a unique pointer to this entity by using the new makeUnique keyword makeUnique function introduced in C++14. And we simply specify the type of the entity we want to create and perfectly forward all the arguments to the entities constructor. Also, we need to get the row pointers from the unique pointers in advance, as we're going to move the pointer into the vector and we will not be able to get the pointer later. So now that we have these two variables, we basically start by adding our new entities to the grabbed entities map by getting the hash code of the type of the entity by using the type ID keyword and the T type and the hashcode method. It returns a std size T hashcode that will be unique for the T type. And we can use that as a key for our map. And then this will return the vector of entities with that specific hashcode, and we place back the normal pointer, the row pointer in this vector. Then we'll move the unique pointer into the entities vector so that it will take ownership of this entity. And to end, we will simply return the reference and return the pointer to give the programmer a reference to the newly created entity. Now, removing of entities will work as we did for the bricks. We don't want to remove them immediately. We want to mark them and then remove them when it's convenient and when it's easy to make it fast and performant. So we'll add a refresh method that will basically look through all the entities and call remove if and deal with the deallocation and destructions of these entities. So we start by doing this process on the grouped entities so that we do not actually deallocate the memory, but only remove the pointers. And we simply take all the pairs in the map. We take the vector, which is the value of the key. And basically, we call the remove if function as we did earlier in the main function. We check if the entity is marked as destroyed, and after that, we will erase all the entities. And then we do the same on the entities vector, which is the owning vector. You may notice that I'm using a const reference here because the element type of the vector is a unique pointer, so I don't want to copy it, obviously, because it's impossible. I'm taking it by const reference, checking it if the entity that it holds is marked, and after that, it will erase all the unique pointers from the vector, and that will automatically deallocate the memory, as we know, because smart pointers are amazing. And after that, we're going to need some useful methods, which will be the clear method that automatically removes everything from the manager. We will also use C++14's automatic function type detection to get all the entities of a certain type without having to specify the long return type. And basically, we manually pass a t parameter to this function, and we get back the vector containing all the entities with that type. And another useful method that we use is a for each method that will automatically get all the entities of a certain type, cast them to references to their type, because we store them with the generic entity pointers, and do something with all these casted entities. So basically, we pass to this method a manually provided t-type, and also it will deduce a tfunc type that can be any kind of function, such as a lambda, functor, or a real function. And we get all the entities of the t-type, and for every single pointer in that vector that is returned from getAll, we cast the entity to its real type, because we're assuming we know what we're doing, with the reference it, and we call the function with this the reference pointer. So it provides a very easy interface for the programmer to do something on all entities of a certain type. And I will show you how it looks in a moment. Then we need an update and draw method for the manager, because we do not want to manually call update and draw on every single entity type. So this will basically loop through all the entities and update them or draw them. It's very easy. Now, in the classes that we had previously, we do not change much code. The only thing we do is obviously specify the inheritance. It has to inherit from the entity base class. And also, a very useful thing to do is to use the override keyword, which was introduced in C++11. And the override keyword basically is put after the name of a certain method. And if it's not actually overriding a virtual method of the base class, it will throw us a compiler error. So we know we're doing something wrong, maybe misspell the name. We do the same for the paddle and the brick, obviously. And now the interesting thing is in the game class. The game class does not know anymore about the game types. It knows only about the manager as it stores it. And in the game loop, in the restart method, we can see how easy it is to create entities with the new manager syntax. We do not have to worry about memory management. We just call manager create brick with the arguments that will be forwarded to the constructor. So as you can see, it's really straightforward. It allows the programmer to not think about memory management. And we do that for the ball and the paddle. It's basically, we are converting the code of the previous code segment to the new syntax. And in the game loop, you can see how easy it is to use the new for each method of the manager. Basically here, what we're doing, we're using C++14 generic lambdas to get all the ball objects in a for each loop. Inside this for each loop, we're gonna call two other for each loops that will allow us to check the interactions between the ball and the bricks, or the ball and the paddles. And all of this, because of the for each method, is done by casting the pointers to the real types that the programmer is specifying here. And basically, this allows us to think about game logic in a very simple way. As you can see, it's much easier to reason about and to alter than it was previously. Let's say we need to add a new brick type. We just put another for each here. So it's very flexible, easy to maintain and expand. And lastly, we need to remember to call refresh on the manager, because this code block will obviously mark some of the entity as destroyed. And here we have to remove actually the entities from the vectors and free their memory. And we simply draw the manager and display the window, and I'll show you that the game should work. OK, the game is the same as before. As you can see, there are no visible difference. but the underlying system is now much more robust. It allows the programmer to add new entity types very easily. So it's obviously a step in the right direction. And we have some more time, so I will show you the optional code segment that basically adds some finishing features to our game. We will add some text objects to tell the player what's going on. We'll add some win and lose status with limited lives, and some special bricks that require multiple hits to be destroyed. So to do that, we do not have to deal with the manager of the game anymore. We simply go to the ball class, and when the ball is leaving the window through the bottom, we set destroy to true. So we're gonna destroy the ball if it falls down and lose a life for the player. Now in the brick class, we're gonna add a new field that it is an integer field, and it is the required hits for the brick. Using the initialization syntax, we're gonna set its default to 1. And basically, we're gonna change the color of the brick based on the required hits. And they have 3 different colors here that basically look one darker than the other, and it will help us understand how many hits we need for a certain brick. Now in the solve brick back collision function, we need to check if the brick is actually destroyed or that if we need more hits. So we basically decrement the required hits field, and if it is lower or equal to 0, we destroy the brick by marking it. In the game class, we add 2 additional game states, which are game over and victory, that will keep track of the win and lose conditions. And also, we will add some SFML very easy to use classes, which are SF font, that represents a font on the user system, and SF text, which represents an object that we can draw and alter a string that will be displayed on the string on the window. Sorry. We'll also need to keep track of the remaining lives so that we can set the state to game over when it reaches 0. So in the constructor, we have something new to do. We need to load this font from file. I'm using Liberation Sense from my fonts folder. And then we're going to use various methods of the text object to set the font, the position, the size, the color, and the string. It's very straightforward. As you can see, the interface is very easy to use. In the restart method, we're going to set the remaining lives to 3. When we're going to set the required hits for the bricks with a simple modular formula that basically lays them in a very nice fashion. Basically, the bricks that require more hits are in the center, surrounded by the simple bricks. And we need to make some more checks inside the game loop for the state and display something to the player. So if the state is paused, we will display the pause string. Otherwise, game over or you won. It's very simple. And then we'll draw the text by using simply Windows draw method. It's very easy. After that, we need to check if there are no more balls on the screen. If that happens, we need to decrease the remaining lives. To do that, remember we had this easy getAll function that takes a type. So we simply ask the manager if there are any elements in the vector of ball objects. If there aren't, it means that the ball was destroyed because it went outside the window. And if that's the case, we need to create a new ball to allow the players to keep playing and also decrease the remaining lives. If there are no more bricks on the window, the state will be set to victory, obviously, because we have reached our goal. And the rest of the code is basically the same, but we have to set the lives text to the current remaining lives. We're going to use the C++11 toString function that basically takes any numeric object and converts it to a string, and we're going to append it to the lives text. And as we run our code segment, we will see that it begins with the paused. By pressing P, we unpause it, and we have our bricks. Some of them take more hits, as you can see from the color. And if the ball goes outside, we lose a life. And when we lose our lives, it is game over. So that's the end of the game. Basically, it's 450 lines with comments, but I believe it's a very simple coding style. It's very modern, so it's easy to expand and to understand, and that's thanks to the SFML library, but mostly to the newest standard that allows us to use this kind of modern style of coding. So this is the end of the talk. Thank you for coming. If you have any question, please use the microphone.
At what point would you probably go away from SFML and use one of the common graphics libraries like OpenGL or DirectX? Is there a limitation on using the SFML?
So the SFML library is very limited in terms of what you can do about rendering. Basically, it allows you to load your own textures and sprites and render them on the window, but it's always limited to 2D. But the SFML library doesn't force you to use. I'm sorry, I had to repeat the question. Basically, what he said is, is there any limitation in using the SFML library instead of more common libraries such as OpenGL? And my reply is, SFML allows you to render objects with that very simple interface, but only 2D objects. That can be shapes or textures that you load in, like spreadsheets and so on. But SFML doesn't force you to use that. So you can use FML for the input management and the window creation, but you can use OpenGL along with SFML to render 3D objects. So it's a very flexible library, and it has some limitation, but you do not have to use the rendering system. You are not forced to do it.
I really like your usage of the modern style. I wanted to ask about the context for ints and floats, where you would customarily just say const int so-and-so. What is the advantage to the style that you chose, other than, is it just illustrating the new style, or is there a distinct advantage to doing it that way?
So I've used the context per keyword basically to demonstrate the intent that that variable is never going to change. It was not required. I could have used const or basically no keyword, but in my opinion, something very important that we often forget is to display the intent of our code. If it is something that is not going to change, we should mark it as such. So it's a simple way to tell the people reading our code that it's not going to change ever inside the code. That's it.
And will you also put back up your information about where that source code can be found? So that we
Yes.
can write that down?
Okay. So you can find the source code on my GitHub page. It's all open source. There are also a lot of other projects that you may want to check out about game development. I have a series of libraries that I use in all of my projects, random utility libraries. Also some wrappers for SFML common stuff, and 2 open source games that I'm working on. One is released, and the other is a work in progress game. And I accept pull requests, so if you want to help me with the development, that would be great. So thank you again for coming. If there are no more questions, we can wrap it up. Okay, thanks everyone.